Assalamualaikum, my name is Rabiatul Adawiyah binti Zulkifli, nombor matrik 201371562. Today I'm going to present about Assignment 2. This is question 1. Based on figure 1, determine the complete sums and intermediate carry C out by analyzing the operation of the circuit in figure 1. The question given the figure 1 and also the data. You need to input the data into the circuit in figure 1 from the LSB to the MSB. Input 1 A1 A is 1 1 1, so put it 1 1 1. B equal to 1 0 1, so input them to the circuit 1 0 1. And then we need to sum it to calculate the C out and sum. A, so 1 plus 1 plus 0. Why 0? Because it doesn't have carry in. So 1 plus 1 plus 0 equal to 1 0. So sum equal to 0, so the carry out 1. Carry out 1 and into C in the second. So for this part, we need to sum 1 plus 0 plus 1 equal to 1 0. So the output of sum is 0, and the carry out 1 into the C in for the 3 for part 3. So 1 plus 1 plus 1 equal to 1 1. So the sum equal to 1 and the C out equal to 1. You can if you want to you can refer to the data sheet of the circuit. Question 2. Given a full adder truth table in figure 1, write sum product SOP for the sum and C out operator. So we need to write the sum of product of the sum and C out of full adder. Based this table, the truth table of full adder. From this truth table, we need to find the SOP. SOP is equal to the output will be 1, and then you can build the Boolean expression from the table. This is the Boolean expression from the truth table, and then the second use Knopf method to minimize the expression, and then draw a circuit by using inverter and OR logic. Okay, from this Boolean expression, we need to draw a KMAC. This is a KMAC for sum, and this one is for C out. After minimize the Boolean expression, the sum is equal to A XOR B XOR C. For the C out, equal to A C bar plus AB plus BC. After we find the KMAC, we need to draw a circuit by using inverter and OR logic gate. This is XOR, so we need to use OR logic with inverter to be equal to XOR. This is the circuit of of the full adder using inverter and OR gate. Question 3. Sketch the 4-bit parallel adder and determine the sum and output carry for addition of the following two 4-bit number if the input carry Cn plus -1 is 0. This is parallel adder is built from the full adder combined with 4 full adder. That's why we call it parallel adder. So this is data given. Input the A into the circuit 0 1 0 1 0, and for the B we input into the circuit 0 1 0 0 1. So and then we calculate the data 0 plus 1 plus 0 equal to 1. So the sum is 1. C out is 0 because this cannot carry, doesn't have carry value. So C out 0 for, and the second 0 plus 1 plus 0 plus 0 equal to 1. So the sum become 1. C out is 0 because it doesn't have carry. And then go to part 3. 0 plus 0 plus 0. So the sum becomes 0. Doesn't have carry. So 0 go to the plus 1 plus 1 plus 0 equal to 0 1 0. The sum equal to 0 and have carry 1. So the C out equal to 1. Question 4. Figure 2 show a block diagram for 4 to 1 multiplexer. Design a 4-1 multiplexer by showing the truth table and Boolean expression. This is the truth table for the 4-1-bit multiplexer. From the truth table, we get the Boolean expression Z equal to S1 bar, S0 bar, I0 plus S1 bar, S0, I1 plus S1, S0 bar, I2 plus S1, S0, I3. From this Boolean expression, you can design the 4 to 1 multiplexer using the quarters. This is a design of the design circuit of 4 to 1 multiplexer. Question 4 again. This is second. Draw a block diagram for 8 to 1 multiplexer using 4 to 1 multiplexer. Okay, this is a figure, the block diagram of 4 to 1 multiplexer. And this is the 8 to 1 multiplexer using 4:1 multiplexer. You use a 4:1 multiplexer combined with 2:1 multiplexer to get 8:1 multiplexer. For question 5, figure 3 show a block diagram for 2-bit comparator which compare two numbers x and y and produce two outputs x greater and equal. The 2-bit comparator will compare the 2 bits binary x1, x0 with y1, y0. The x greater output is at logic 1 when the value of x greater than y. Meanwhile, the equal output is at logic 1 when the x is exactly equal to y. Design the 2-bit comparator. Okay. This is the design circuit which is using quarters of 2-bit comparator. And then this is a truth table of the truth table from the design circuit. From the truth table, we can draw a K map, and then we can find the expression of the x greater and also equal. Question 6. Design a decoder that accepts 3-bit input and display alphabet at the 7th segment as illustrated of figure 4. The input-output mapping is shown in table 2. Design a decoder. We need to design a decoder. The example of decoder using 3-bit, which is x2, x1 and x0. We need to display the alphabet in the table 2. This is the design of the decoder that accepts 3 bits. Last question, based on figure 5, draw the output waveform in proper relation to the input. This figure 5 shows that they have given the circuit design and also the waveform of the data need. It's a lot easier if you go to the quarters and design the circuit from the figure 5, and then you input the data of the waveform. And if you simulate, you can find the output of y. This is the theoretical output form. It is a simulation. It mesh with the theoretical